recording. Oh. So we take feed out. The morning does have it recorded, so that will get posted. I'll post both links. Sorry.
It's all right.
I think I did a better job talking to you guys, though, so sorry. So B, 0.127 feet we can't use.
Are you recording now?
I'm recording now, yeah. After I talk about how much I screwed up. It's a good way to start a video. With the other options, is there anything else you could eliminate? Why D? Right? Would we ever expect it to get bigger for a covalent bond? Okay, our atomic radii are nice and set up. If they're going to interact with each other, more than likely they would come closer, but at a first approximation we could say they stay the same. Okay? Why would they ever get further away from each other? That's the complete opposite of what we would predict for a bond. So DE doesn't make sense.
And E doesn't because it's smaller.
E doesn't make any sense because it's so small, it's actually smaller than the radius of a hydrogen atom. So somehow or another we took two atoms and bound them to each other and made them smaller than the smallest of those two atoms. Okay, again, doesn't make physical sense. Okay, but now we're left with a problem. How do we decide between A and C? Because we announced in class that what happens with a covalent bond? It decreases from the sum of the radii, which means it can't possibly be our 0.136. It has to be our 0.127.
Okay, so we use the formula that is in the book to determine the covalent bond, whatever radii we're thinking
To
about.
convert or to determine the maximum value.
Yeah, and then we have to go, like, we'll see that on as one of the questions, but we need to go a little bit lower than that.
You need to go a little bit smaller than that
So
because for a
probably
covalent bond, it definitely shrinks.
Approximate.
It's approximate, yep. So would I ever put on there as an option 0.124 nanometers? Okay, I hope not too. Okay, I don't expect you to be able to predict how much smaller it gets as long as it's not ridiculously smaller. Okay, so as you can see with these examples, we tried to pick the extreme cases. Okay, questions about that?
So that would be a good rule of thumb to think it's going to be a little bit smaller than the
Yep.
radius?
It's a little bit smaller than the sum of the radii. Exactly right.
But we have to recognize that it's a covalent bond, just as an element. Or would you ask?
Probably not directly for this question, but should you be able to tell me, based on the elements, that it's a covalent bond?
Yes.
Yes, absolutely. You need to be able to do that to do what? Nomenclature. So you should already be able to determine that if we take hydrogen and chlorine and bring them near each other, we classify that as a covalent bond. Okay? Because neither of them are metals. Okay? So for that question, I would probably tell you that it's covalent, but you should be able to predict. Oh, this is a bad idea. I'm not doing that way. Okay, so questions? Do it that way so I don't walk around you. Let's take a look at bond energy. Okay. What would we expect to happen to the energy if we made a bond? So this is a trickier question. Would we expect our overall energy to go down, up, stay the same?
Expect it to go up.
Be neutral.
So if we start with two separate atoms, and we go together to try and make them a bond, if that bond is higher in energy, is that more stable or less stable? Less stable. What are your atoms going to do? F this and split back into the atoms. I don't want to be higher energy, I want to be lower energy. Okay? So we would not predict a bond to be higher in energy than the individual atoms. Okay? What about the same energy? I mean, that's not bad, but then we decide, well, why we'd end up with a whole lot of mixtures of pretty much equal not bonded and equal bonded. And we don't really actually have that either. What we really have are most of our atoms are found in molecules, or in bonds. So what does that predict as far as our guess? we would expect our energy should go down. So if we looked at the energy, and we'll just decide some random numbers on this, the energy of our starting materials to say 100 joules, what would the energy be of our product molecule? Less than that. So let's pick a number nice and extreme, 1 joule. What's the change in energy now for this reaction? How do you calculate a change? You subtract. Which do you subtract? 100 minus 1 or 1 minus 100? Does it make a difference in your number? You should say yes, because otherwise we can go through and do a trade. I'll give you $1, you give me 100. Okay? It's a pretty big difference. Okay? So which do we subtract from which? Our change, by definition, is always final minus initial. Okay? It's again kind of a definition thing, so we just got to decide. What was our final energy? 1 joule. What was our initial energy? 100 joules. What's our answer? Negative 99 joule. That's not a J. Wow. What does that negative mean? We lost energy. Okay? Think back to chapter 1 or 3 or one of those earlier ones. There was a rule that we came up with, or a law. That law was the conservation of matter and the conservation of energy. We cannot create or destroy energy. So as we've described our reaction, our molecule may have lost, or our atoms may have lost energy to make that bond, but that energy has to be accounted for in our reaction. Where do we put the energy into our reaction? Was it a reactant, or was it a product? It's a product. It was energy lost in the process of doing that reaction. So we would put plus 99 joules. What happened to the minus? The minus tells you that that energy term was a product. That's all the minus tells you. Mathematically, it has to be there if we're going to look at equations. But as far as our chemical understanding, that just means that that much energy, 99 joules, was a product. It was released in the course of this reaction. Okay? Yeah?
But wouldn't it also be a product if you add energy to it?
So if we add energy into it, what happens? Now our atoms absorb that energy. The energy of our molecule has to be higher. Okay?
Oh, wait, I get it. It was always up and down.
So if we had added energy into it, we would have had, say, 99 plus 100. What would the energy have been for our product? Would have needed to be 199 joules. What would our change in energy have been for the reaction? Okay, so let's erase all that. So now we say we don't know the energy of our product, but we know that we put in 99 joules of energy. According to conservation of energy, what's the energy of our product? Has to be 199 joules. Okay, we have to make sure our energy balances across the reaction. What's our final minus initial? Okay, so if we ignore the energy that we put in, so our final minus initial will always give us 0 if we're looking at the whole reaction. Let's look at just the atoms now. Okay, just the atoms. So our molecule, our final energy was what? 199 joules. What was the energy of our atoms? What's the sign? Plus 99 joules. What does the plus mean? That energy had to have been a reactant. What did we start with? Our initial assumption was the energy was a reactant. The plus sign means our energy is a reactant. The minus sign means the energy is a product. Okay? Those signs imply chemical information that we can either choose to interpret, or we leave it as just a mathematical symbol and you memorize the meaning of it. And you hope that you don't mess up the symbol. Okay? So let's get back to the point. All bond formation will release energy, every single one. If we start with our atoms, we will release energy to make a bond. Okay? What's the result of that? Well, we release that energy in the form of heat. Is heat a form of energy? Yeah. Okay. What would that reaction be defined as according to your bugle and macadamia nut experiment? I think it was that one. Exo or endothermic? It was exothermic. Heat left the system. What happens if instead of looking at forming that bond, I look at breaking it? What would I expect the sign to be on my energy? Positive or negative? So what we're saying now, I want to do the reverse reaction. What are my reactants? The molecule and heat. If heat is a reactant, that means we are absorbing heat. What does that mean the sign is? Positive, because it's on the reactant side. If it's a reactant, we can't call it exo anymore. We call it endothermic. Okay? So we could now, oh, come on. So we could look at those two equations as relationships. Okay? Ultimately, we're looking at the same number in both cases. If we released 99 joules of energy to make the bond, we're going to have to absorb 99 joules of energy to break the bond. Okay? What's forward must be the same in reverse, okay, as far as the magnitude goes. Okay? Now the interesting question is, if we're going to try and put this into another equation, and we want to form tables of this information, what value do we report? Do we report just 99 joules? Do we report negative 99? Do we report positive 99? Is that going to change how you would manipulate those numbers in your calculator? If you did negative 99 versus positive 99, that should give you a pretty substantial change. So we need to make sure that when we define and use these numbers, we have to understand exactly what they're referring to. The bond energy is now defined as I turn around to read the slide, the required energy to break a covalent bond. What should the sign be for your bond energy? Positive or negative? Which reaction breaks the bond? Top or bottom? Which one results in atoms, so the end of the reaction, with atoms as opposed to a molecule? Bottom. So the bottom one is the breaking of our bond. Where was our heat or our energy term in our bottom reaction? Is it a reactant or a product? It's a reactant. If it's a reactant, is it endo or exothermic? Endothermic. What's the sign? Positive. Okay. So we're looking at an absorption of energy. If you absorb something, what happens? We absorb enough food, what happens? We get bigger. If we lose, well, that's not particularly pleasant, but if we lose enough food, we get smaller. Okay? Kind of, sort of. Close enough. Okay? Are all bonds the same? Okay? No. Very least, we've got covalent, I want to start with ionic and covalent. Okay, this slide should have released some information in here, or broken it down a little bit more. So we've got two primary categories. We've got ionic bonds and covalent bonds. Okay, well, what was an ionic bond? What was the rule that we used? Metals and nonmetals. Turns out that definition is not perfect. Okay. It's really referring to ions being present. Okay, and typically that's a metal and a nonmetal. which is why when we look at ammonium, we lose our definition a little bit. Okay? So what we want to do is expand that definition to make more sense or involve more things. Problem with expanding the definition to include better categorization is that it typically requires more information. For it to be an ionic bond, okay, what we're looking at is that one of those atoms takes the electrons away from the other atom. Okay, so what we're doing is comparing those two atoms. What about the two atoms in that bond are we comparing? Their ability to attract electrons, in fact, bonding electrons. Did we come up with a definition of something that defines the ability for one atom to take electrons from another atom? Say last Thursday or Tuesday. Begins with an E. Rhymes with positivity. Electronegativity. Okay? So what we can do is instead of using this broad definition, we can go in and look at electronegativity to determine what's happening. And what we're going to define our ionic bond to be is the difference in electronegativity between the two atoms. If that difference is larger than 1.7, it is an ionic bond. Okay, very strict, cut and dry. That's kind of nice. Problem with that. What's the electronegativity of carbon? No one. Silicon? Nitrogen. Oxygen? Hydrogen. Helium, lithium, potassium. Sorry. Okay. We don't know those, or you don't know them. I don't know them either, for that matter. Okay? So, to use that definition, we've got a bit of a problem. We either have to come back and now tell you, remember that table of electronegativities, memorize all of those more numbers with each of those atoms. Okay? You got enough stuff to memorize? Yeah. So don't memorize it in that respect. Remember that your ionic bond is going to be a bond between a metal and a nonmetal. Okay? If I go through and give you a list of electronegativities and say, classify the bond between two atoms within that list, you should be able to tell me that it's ionic because you now have that difference. Okay? Your textbook is going to ask you to do things along those lines. The ionic ones probably won't get asked because it's very clearly metal and nonmetal. Really, really easy and simple to do with that definition. So why bother to deal with the math? Where the electronegativity difference plays a much larger role is when we go in and look at the covalent bonds. We said that there had to be different types of covalent bonds. Remember water versus HCl? Okay. Both of those were non-metal bonds, but we end up getting very drastically different results, okay, as far as the chemistry goes. So what's different in those results? Okay, so what we're going to do is actually categorize covalent, subcategorize it into two separate compartments. Nonpolar covalent and polar covalent. Okay, what is that polar referring to? Have you ever heard of polar before? There's a North Pole and a South Pole. Okay, the north is on one end of our planet and the south is on the opposite end. So they're ultimately opposites, right? We've seen opposites before in, say, bonds. Like maybe a positive and a negative in an ionic bond. That is, it's not even that, we're just looking at polarity. Polarity just means we have a positive and a negative. Okay? So our gradient here is that we look at ionic as our extreme version of polar. It's so polar that we actually have ions. Nonpolar covalent is the complete opposite. A nonpolar covalent bond is I take two atoms, say hydrogen and hydrogen. Would I expect there to be any polarity associated with it? Would I get a positive and negative aspect to it? No. Why? Why? It's not just the same atom. There's a little bit more I want in that. Goes back to what you were trying to start. What's the electronegativity of hydrogen? Well, let's pick a number. Let's say 1. What's the electronegativity of the other hydrogen? It's also 1. What's the difference? 0. Which means they are equally sharing electrons. Neither one or the other is positive or negative. There is no separation in charge. We get exactly 0, 0, complete and equal sharing of electrons.
Is that why they're only double bonded?
It's not a double bond. Different reason. All right. So what else could we go through and do? Nonpolar covalent then is a very, very narrow definition. We're bonding something that's the same, not charge. There's no charge in covalent bonds. Okay. Same to same. That's going to be a non-polar covalent bond. So we could take the most electronegative element. Anybody remember that one? Oh, you guys are going to need that. The most electronegative element. Fluorine, upper right corner. Most electronegative element, and I bond it to another fluorine. We got wicked high electronegativities. Typically, we bond fluorine to anything, and we're going to see some polarity associated with it. But if I put fluorine next to fluorine, what happens? The electronegativities cancel, and I get nonpolar covalent bond. So it's all about that difference between those. It's not just that one's really high or one's really low. Problem with that definition is it's very, very, very narrow. Okay? So we're going to expand that definition ever so slightly, and this becomes more important for organic chemistry. It's not just same and same, but we will also categorize the carbon and hydrogen bond as a nonpolar covalent bond. And that's because the electronegativity of carbon and hydrogen are very, very close to each other. Okay? So those would be our general rules. The super accurate, gnarly specific rule, the difference in electronegativity must be less than 0.5. That's where that number came from. Okay? So we've got ionic, metal and nonmetal. Now nonpolar covalent, anything that's the same bound to anything else that's the same. And then carbon and hydrogen. How many bonds or molecules have we accounted for there? Maybe 20%, 30% of our possible molecules. Okay? Probably closer to 5% of our organic molecules. Actually, it's even lower than that. So life itself is now not described by polar or nonpolar covalent and ionic. Right? That's a pretty crappy definition. So what's left in the middle? Polar covalent. What is polar covalent? My favorite definition. Okay. If you were in organic chemistry, we narrow that a little bit. And the reason we get to narrow that a little bit is because in organic chemistry, I don't care about 90% of the periodic table. Okay? I got 10 elements, and that's what I'll stick with. Okay? So we can really zero in on just what makes it polar covalent versus not. Okay? So we now have ways that we can then classify these individual bonds. If we're going to name a polar covalent bond, what rules do we use to name it? That one's a little bit different. It's named the same way as we would name covalent bonds or binary molecular bonds. We want to use what the lab is calling it. Okay? It's the exact same methodology. Okay? The only reason that we subcategorize it is because our chemistry changes drastically within it, and we can introduce a new notation. Okay, so let's clear all this. So I can write nice and big so we can see a new example here. Let's take a look at our HCl bond. I really don't think I'm writing that big, but everybody seems to laugh that I am. I guess that does look pretty big. Okay, HCl. Okay, we're representing the bond as that dash between them. We'll talk about that dash in just a little bit. Where does that electron, it's a C and an L, give me a break, it's cursive. Where do the electrons in that bond spend most of their time? I could kind of accept that. Let's push a little bit further. Which atom do they prefer to spend their time with? Chlorine. How do you know that? I'll accept two reasons. What was yours, Roshan?
Oh, CL will take away from
Chlorine's charge? -1. So it's probably going to take electrons from hydrogen. What's hydrogen's common charge? +1. It's willing to give those up. Okay, so I can kind of half-heartedly accept that one. There's a better one.
It's on the dash.
No. Electronegativity.
Oh.
Okay. The difference in electronegativity between those. Chlorine is much more electronegative than hydrogen. What does electronegativity measure? The amount that it holds bonding electrons. So what we're saying is that some of the time chlorine takes those electrons and it holds on to them. Okay, well, in those cases, when it holds on to those electrons, what charge does it become? Chlorine gains electrons, becomes negative. If it was negative, though, it would be an ionic bond. It's not ionic. So we can't really say negative here. Okay, but before we scribble it all out, what we want to do is say, but it is negative. It has some negative characteristics. Okay? To address that, what we'll do is say, well, it's, come on, partially negative. And we use a lowercase delta symbol to represent that. Okay? Why delta? What does delta mean? Change. What are we looking at here? A change in the location of our electrons. Okay, so all it is a new notation to say that that chlorine becomes a little bit more negative. But if it becomes negative, what happened to the hydrogen? It had to become positive. But is it actually fully positive? No, it's only a little bit positive. So we use that delta symbol to represent that it became partially positive. Okay? The importance in this. HCl, as we generate these charges, starts to approximate or look like an ionic bond. So we might expect HCl to react similarly as if it was an actual ionic bond, even though the electronegativity difference isn't there. Okay? So we can start to predict something about that chemistry. The next big issue to address with this, we've defined covalent and ionic and polar covalent. And in each of those cases, we said pretty much black and white covalent is this, ionic is this, polar covalent is this. Is that true? No. When does it change from being red to orange in a rainbow? Can you tell me that line? No. It's a continuous spectrum between those colors. Bonding is much the same. We go from one extreme, complete sharing of electrons, to completely not sharing electrons. Everything in between is some spectrum within it. And we put names on it, just like we do with the rainbow. Do we look at the rainbow and say, oh, I see rainbow? Oh, I see red, I see yellow, I see orange, I see green. Why do we say we can see those colors? Much the same way that we're seeing and defining these bond classifications. Okay? So realize that you can push and make compounds that you would expect to be polar covalent. Though if you look at their electronegativities, they actually end up being better defined as ionic. Okay? Yeah.
What do you mean, like the hydrogen chloride or whatever, it looks like it's ionic, because aren't those both non-ionic?
Well, so ionic has positive and negative charge. What charge builds on the chlorine and the hydrogen? Positive and negative. What charge builds on our nonpolar covalent? Nothing. There is no difference in electronegativity. There is no charge. So if I'm going to try and classify how HCl is going to react, would I expect it to react where there's no charge or where there is charge? Where there is charge. Okay? So that's why we look at those differences in electronegativity, because it allows us to predict something about their reactivity. Okay? Last little notation that we'll put on this. There's one more thing. I can't remember if the textbook showed this or not. You can sometimes see an arrow. And it is what this arrow might be showing.
Where the electron is sharing to.
Where the electrons are moving to. So we are showing that the electrons are moving towards the chlorine. How else can we see that? What does this symbol look like? Plus sign. So we put our plus side of our arrow where our atom is most positive, and the electrons move towards the negative side. Okay? It's just another way to represent the molecule. It's all it ultimately is. It's nothing particularly special or interesting beyond that, other than, hey, we can now see some of that chemistry. If we completely ignore that plus and minus charges, or those partial charges, then we lose an understanding of how HCl reacts in a real world situation. So we want to accent that information by putting those partial charges on it so that we can interpret a little bit more. Okay? And that's all those are. Just a notational thing so that we can see it. Okay? Questions about that? Okay, so now in for the...
Can you give us like a test question as to like how you would make us demonstrate our knowledge of that? Sorry.
No, that's fine.
I just don't know.
Provide the partial charges. Place the delta positive and the delta minus over the appropriate spots.
Positive would be on the hydrogen.
You would then draw in a short answer situation, delta positive, delta negative. Why did you decide to put it that way? Again, two answers. What charge does oxygen typically carry? Negative. Okay, what charge does hydrogen typically carry? Positive. Why does oxygen carry a negative typically? Because it's more electronegative than the atoms it's typically bound to, so it takes the electrons away. It becomes negative. Okay? So it would be a short answer drawing something on it. Okay? There's no work, you just draw the answer.
So it'll be like with our dot structures, we'll have to do something like this.
You could potentially do that, yes.
Or there could be an extra credit, especially.
Yep, could be.
So that's all it would be.
Yeah, there isn't anything else I can ask. Yeah, with that symbol notation, that's it. Okay? You guys are all panicking. It's just
Say that
it's
one
just a
sentence
simple.
again, it's more electronegative.
More electronegative is going to take electrons. So the more electronegative it is, the more negative it will become. Lewis structures. Okay, so Lewis came through, took all of our understanding of atomic structure, and he tried to explain a variety of different bonds that could form. Okay? Why do we have the different molecules that we do? Why do we have the ratios that we do? Okay? So when I bond hydrogen to hydrogen, why is it just hydrogen-hydrogen and not, say, H3 or H4? Okay, so he's trying to predict, based on the understanding of atomic structure, how these molecules come together. Okay? So first off, what do you think he's going to look at? Protons, neutrons, or electrons? Electrons, because we're looking at the valence electrons, because those are going to be the first things to overlap between any two atoms. Okay? So we could start with hydrogen. We've got a 1s1 and a 1s1 on the other one. What happens when we bring these two together? Yeah, why not? 1s2. We can put those two electrons into the same orbital. Each orbital can hold 2 electrons. Boom, there it is. Matches up. Beautiful. Done. Explains it. What happens if we make it more difficult? Think about what the next slide shows. If we jump to HF. Yeah, the next slide's got it. Well, we could look at our electron configuration for HF. 1s1, and we look at our highest energy level for our fluoride. Again, we want to look at our valence shell, and we're looking at the 2s and the 2p. How many electrons can fit into fluorine? How many more electrons can it take? 1. So what happens? We take the electron from hydrogen and we slide it into that one spot on the the fluorine. Okay? So we went through and said, okay, for each of these energy levels, and we could look at carbon's electron configuration and nitrogen and oxygen. We're looking at that second energy level with 8 electrons. I don't have enough fingers. 8 electrons in it. So we thought, okay, what shape has 8 points? A cube. I don't know why he thought this, but this is what he did. His paper's kind of bizarre. Okay? And so he went through with, say, our HF, and he put in hydrogen in the center of these. And he put fluorine in the center of the other one. And he went around with fluorine and put on its electrons. 2, 3, 4, 5, 6, and 7 valence electrons. He said, on these cubes, now what happens? I can then overlap these those two line up, and now I have a bond between hydrogen and fluorine. He went through and did this very oddly for CH4 and NH3. Okay. We then went through and looked at that and said, that's a bit odd. I mean, right? Do we really want to have to draw out cubes for larger molecules? No. So what we did instead is simplify that for 2 dimensions. What's the most likely or easiest way to represent a cube, but only in 2 dimensions? A square. So he took fluorine and our hydrogen, and he said hydrogen comes in with 1 electron, fluorine comes in with his 8 electrons. Why alternate instead of doing pairing right away?
Make it even.
There's a better reason. How many electrons can fit in an orbital? 2. So let's fill our 4 sides of our square, okay, with a single electron before we start pairing. Okay, now what happens? I have 2 electrons between atoms. So I will turn those 2 electrons into a bond. Ta-da! I now have HF. I have the bond, or the molecular structure for this compound. And he went through and he did it for other elements too. Say methane.
So is this the Lewis structure?
This
or
is
the electron
it's
dot?
the same thing.
Okay.
Lewis is giving credit to Lewis. Electron dot is just being a jerk. I was recording that too. That's good. Okay. Hydrogen each comes in with 1 electron. Our carbon comes in with 4 valence electrons. Now what happens? They have a party. We form the bonds, and we now have methane. Okay. 4 bonds, each of them to our hydrogens. Okay. All he was trying to do was to describe the atomic structures and come up with ways to predict what was happening within these.
So that's CH4.
That is CH4. Why did I pick 4 electrons for carbon?
'Cause that's what
No. What was your answer?
That's what would have bonded them.
Where did we start this whole argument with? Big hint. For hydrogen, I had... Why did I give carbon 4 electrons? What are the valence electrons for carbon? How many is that? 4. Why did I give carbon 4 electrons? Because that is its valence electron count. Okay, so you need to be able to count your valence electrons. How do you know what your valence electrons are?
So you only do this based, you only use their valence electrons.
You only use the valence electrons to do this. How do you determine your valence electrons?
The highest level.
The highest energy level using electron configurations, everybody's favorite. Okay? There are shortcuts, and you can use shortcuts if you want, but you have to be able to predict those valence electron counts.
So is it the 2 last valence electrons? Or?
It's going to be the highest energy level.
Okay.
So why do I count both the 2s and the 2p as the highest energy level? What's the energy level? It's the 2 energy level.
So if it said 3, you would count the S and the P and the D.
And the d, which brings in a whole other can of worms. We aren't going to bring in the d orbitals.
So the highest energy level is
1, 2, 3, 4, 5, 6, 7. 7 is your highest energy level. Okay? So, coming up with rules. These rules, I'm going to tell you right now, everybody has a slightly different spin on how you draw Lewis structures. Okay? This looks like a lot. This is incredibly important, and we still have time. Okay? These rules will guarantee that you get the correct answer if you follow the rules.
So we have to memorize them?
You need to be able to use them. You either memorize them or you can memorize another process. Most of these rules become internalized, both from the tutors and other instructors. Everybody has a slightly different take on it. Your textbook organizes the rules slightly differently as well. Find whatever rule set works for you. I use this rule set because steps 6 and 7 become obvious if you use step 6 and 7, if you follow these rules. The next big important point to notice, rules 6 and 7 will not be on exam 2. Okay? Those are probably the harder aspect of these. Okay? So to start, you need to go through and look at every single atom in your formula and figure out how many valence electrons it has. Okay? Total those. The next thing you got to be aware of is count charges. If your molecule is charged, that means the electron total is different. If it's positively charged, what did you do? You removed an electron. Subtract an electron from your total count. If it's negatively charged, what did you do? You added an electron. What if it's -2? You added 2 electrons. Okay? You have to account for those differences when you look at your valence totals. Now you want to choose a central atom to act as your connector or bridge. It's usually the least electronegative. There's electronegativity again. Really important concept. Okay? The one exception to this is it's got to be something that can bridge. Okay, what do I mean? To bridge, what do? We connect 2 sides, which means we have to have how many bonds? Minimum. 2 bonds. Hydrogen cannot act as a bridge. It will never be the central atom. Okay? You then want to go through and add electrons in pairs to the most electronegative atom first. Why the most electronegative atom? What does electronegativity measure? The ability to hold bonding electrons. We're trying to describe the bonds. Our most electronegative atom is going to take the most of the bonding electrons. That's its job. Okay? So put them there first. You can then continue to add electrons until you've satisfied the octet, which is effectively our noble gas rule. Why do we want 8 electrons around our elements? Symmetry, look at the noble gas configurations. Your noble gas configurations in the valence shell, 8 electrons. Okay? There are weird exceptions to that. Hydrogen, how many electrons do we want around hydrogen? 2 electrons to fill its orbital, that at 1s orbital. It can only fit 2 electrons. Okay? You'll then continue to add your electrons around and then convert any pair of electrons between atoms into a line to represent that bond. Okay? That is officially time. I will continue to talk over you while I do an example here with the NH4. I abbreviated the rules so you can go through and look at these as well. We'll start with our NH4+. Nitrogen has how many valence electrons? Nitrogen comes in with 5 valence electrons. Hydrogen comes in with how many electrons? 1. There are 4 of them. What's the charge signify? A plus charge means I need to remove an electron. Total it up. What do we get? 8 electrons need to go into my structure. 5 plus 4 minus 1. We now pick my central atom. Can't be hydrogen, so we'll start with nitrogen. Arrange our other atoms around it. And now put electrons in on the most electronegative element first. In this case, that is going to be nitrogen. We can put them in pairs. We've now accounted for all 8 valence electrons. Any place that we have 2 electrons between atoms, we can now erase. Another reason why students don't like my method. It's a lot of erasing. And turn it into a bond. We now have the Lewis structure for NH4+, almost. We have the Lewis structure for NH4. How do we know this is plus? Ta-da! Now it's plus. Okay? If you got questions on Lewis structures, feel free to ask.